All right, so here we are after the period of a circular orbit. I'm sorry, I can't think about what I'm typing and say it out loud at the same time. It's kind of funny. All right, so the period of a circular orbit. I just realized I've got a misspelling in there. All right. So let's see. The important thing to realize is if we're talking about a circular orbit, then it's going to be uniform circular motion. And the key thing about uniform circular motion is that the speed is therefore constant. And that gives us a wonderful way of getting at this. It means that the distance traveled will be equal to the rate it travels at times the time, which is just a formula you probably learned about probably way back in like Algebra 1, Algebra 2 days. I seem to recall spending an awful lot of time thinking about these rate problems at some point. All right, regardless, we just need to think about basically distance equals rate times time. So let's imagine we have our central object again. It has some mass. There's an object that's orbiting around it. We know the distance between them, and it sweeps out a circular path. What is the length of that circular path? Hopefully you were thinking circumference, so d is going to be 2 pi r. Okay. V, well, that's something we already figured out how to work out. We'd use the gravitational force again, and we would think about minus g mass central body, mass orbiting body over r squared minus g, mass of the orbiting body, speed of the orbiting body, and v. Cancel, 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 cancel. And we find v would be the square root of g mass of central body over r. So we've got our rate, and we've got our distance. That means we can find our time. So distance divided by rate will give us the time, the period. And that means the period is going to be 2 pi r divided by the square root of g mass central body over r. We can take this r and move it around a little bit. We can take it inside of the square root. So if we square it, we can bring it inside the square root. As for the square root, we can do an invert and multiply with it. And that will give us the period is 2 pi. And then we'd get the square root of r cubed over gm. Okay, so to wrap it up, period would look like 2 pi over the square root of gm times r to the 3/2. And that is just simplifying down the previous statement a little bit. All right, this is going to be related to Kepler's laws, particularly to Kepler's third law, so we'll talk about this equation a little bit more. And effectively, we've just proved Kepler's third law for circular orbits, but we'll talk about that again in the Kepler's laws section, which is Unit 3.8. All right, up next, we're going to try a problem where we'll use a couple of these ideas to figure out something about the energy required, I believe, to take an object from a low Earth orbit to a geostationary orbit. All right, so see you in a bit.